All right. So hello everyone. So this is the last course. I mean, let's say the last course, the last formal course. Okay, but what I propose is that. So today we will do the last thing, which is to understand soft max regression. Okay, which is the generalization of logistic regression to more than 2 classes, okay, to an arbitrary number of classes. Okay, and then I would like to spend a bit of time with you, at least the ones that need to pass the exam. So I guess that's essentially just the QLS students to discuss the project, to make sure that you understood what I would like you to do, and for those that are interested to do the numerical project with or without a mark, it's you are more than welcome to try by yourself. I think it's a very useful exercise. It's not hard, what I'm asking. So we'll discuss that a bit, and then what I propose is that for those who want to go a bit further and know more about neural networks, and I propose the following, is that you read that book, okay, that you can find on internet. It's called Neural Networks and Deep Learning, which is this online book. It's very well written, okay, it's very simple. You see the chapters. This chapter 1, and you read like this. It's I mean, you can read that in front of the sea. It's like a book, okay. It's very simple to read. It's very nice. So what I propose is that you read that. You see the chapters are not too long. It is really only the essential, and at the same time, it's more than enough to understand what is going on. By the way, all the first part will be things that you essentially know, because this is connected to logistic regression. Okay, logistic regression can be seen as what is going on in a single neuron. Okay, you read these things. This is one chapter, for example. It looks long, but it's not. It's easy to read. Okay, the first chapter is maybe the longest. There are 6 chapters. Maybe in total it requires 5 hours of work, 6 hours. And what I propose is that we then do sessions, okay, or we meet or on Zoom, and we talk about the chapter. Okay, you ask me what was not clear, and maybe I can summarize a bit what has been said in the chapter. Okay, does that sound okay for everyone? Okay, perfect. So now that this is said, let's go back to the course. Oops. No. No. Yes. So let me just summarize what we said the other time. Okay. I just recap. Just recap what we said. Okay. So we talked about logistic regression. Okay, and logistic regression means what? Means that you are assuming a model of this form, okay, where you relate the samples, the labels, which belong to some discrete set, okay, and the rule that you assume connecting sorry. What we assume is a probabilistic model. So what we assume is that the probability that a certain label is 1. Okay, we can take binary labels. Let's say 0 and 1. Okay. Given our parameters theta and an input xi is given by the logistic of the inner product, so the projection of the sample xi on the hyperplane theta, okay, on the orthogonal vector of the so theta is not normalized, but on the vector orthogonal to the hyperplane, which is the boundary decision. Okay, again, this theta defines some plane, okay, here in R2, and depending on the sign of the projection of a sample onto this vector, you are on one side or the other of this boundary decision. And the closer you are from this boundary decision, okay, the closer this probability will be from 1/2, because this logistic function sigma s looks how? Looks like this, and it is 1/2 in 0, okay? And it goes to 0 in minus infinity and to +1 in plus infinity. And therefore, the output of this function can be interpreted as a probability. And essentially, the closer a point is to the boundary decision defined by this vector theta, the closer to 1/2 will be this probability. While if you are very far from the boundary decision, okay, this probability will get closer to +1 or to 0, which means that you are very sure that if you are close to 1, this probability is high. So your point is far from the boundary decision, and you are very sure that it should be in the class 1. On the other case, if this probability is very close to 0, which means that the inner product between your vector and theta will be a very negative number, then you are far from the boundary decision, but in the other direction, and this probability is close to 0, which means the probability of being equal to 0, okay, if this thing, okay, this is 1 minus the probability of being 0. So therefore, if this probability is close to 0, it means that this probability is close to 1. Therefore, you are very sure that your sample should be in the class 0. Okay? Okay, so this logistic regression gives us a measure of uncertainty or certainty about what should be the class or not. Okay. Then we discussed how to find these parameters for our model. Okay. And what we showed is that a way to choose this parameter is to maximize, or let's say minimize, if we take a cost minus the log likelihood of our samples given theta and x, but the likelihood of which model? Okay, this likelihood is what? This function, you can think of it as a cost function that depends on theta, okay, at fixed value of the data. Okay, it's just a cost function. And this is the likelihood for which model? For a model in which we assume that the samples, okay, if we take the logistic regression as our model, what does it mean? Implicitly, we assume, okay, the assumption behind logistic regression is that the samples really were drawn according to this probability distribution, right? This is what we assume when we take logistic regression, which means, okay, that the likelihood of the whole set of the whole vector of labels given theta and the inputs, because by assumption, as always in machine learning, we assume that all samples are independent. Okay, we have a product over the samples. Okay, and this, we understood that a compact way to write this, okay, is sigma so if yi is equal to 1, then we should count the probability like this. Okay, so we have a yi here. If instead yi is equal to 0, we should have 1 minus this probability. So it should be the probability of being a 0. Okay, so 1 minus sigma 1 minus yi. Okay. This likelihood here is clear. Okay. 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 And then, therefore, the log likelihood, you take the log of that, and the cost function is minus the log of that. And therefore, it is sum over I of minus yi log of sigma theta t xi minus 1 minus yi log of 1 minus sigma theta t xi. Okay, this is our cost function, which is called the cross entropy. Okay, so this is essentially what we did. And then we took the gradient of this cross entropy with respect to the parameters to get an equation, an update equation that we can use in SGD. Okay, you remember the gradient of this cost function with respect to theta. We showed that it was the sum of yi of sigma theta t xi minus, sorry, here it's xi minus yi. Okay. And this will be important when you will implement stochastic gradient descent. Okay, you need the gradient of the cost function. Okay. Okay. Okay, here, maybe this notation confuses you, I don't know, because here what I define is the probability of a label being equal to 1, while here I write just the probability of the label. Really what I mean here, some of you were confused by that, or maybe I will make you more confused if I try to explain. Let me try anyway. Here, what I should really write to be clean, to be more clean mathematically, is the probability that, let's say, the y's that I think as random variables, okay, which are the random labels, take the value, let's say, little y, which is the actual vector of labels that I measured, okay, is the product of these probabilities. So here capital Y means that I think of it as a random variable, and the little y is the actual realization of the random variable that I observed, okay. Okay, so when when my label I is equal to 1, indeed I should have this, which is what I wrote here, okay. If now I think of here, I should put the random variable yi, okay. While when my yi is equal to 0, I have this contribution, okay. But more compactly, I was just writing this, but it means the same. Is it clear? Or you are more confused now? It's okay? Okay. Okay. Great. Now, then we discussed logistic regression, and we applied that to the Ising model to classify we learned from samples from an Ising model at different temperature, and we tried to classify whether the configurations were above or were samples from the Ising model above or below the phase transition temperature. Okay, so we discussed that in detail, so I recommend you to really understand that example. It's important. And I mean, it's just not an academic example. Huh? People write papers on these kind of things. Huh? So. All right, so now what we want to do is to generalize all that and to consider that the alphabet, so the samples, belong to an alphabet which is not anymore just 0, 1, but you can have more classes, okay? Let's say M classes, okay? So each class in this case is indexed by an integer between 0 and M-1, okay? So to that, you need to use what we call softmax regression. Okay, so what is softmax regression? It's not complicated once you understood logistic regression. It's very similar. It's almost the same. Okay, so the first thing we will do is to use, and actually this is arbitrary, okay, you could, okay. I will follow the notes. This is not my favorite presentation, but this is how they present it. But okay, we will represent not, okay, this is one possible representation. Okay, you can say that the labels are indeed an integer between 0 and M-1, and this represents M possible classes. Okay, another way to encode this information, an equivalent way, which may be more practical from an implementation point of view, and also to introduce the softmax regression, which is totally equivalent, is what we call one-shot representation, okay, or one-shot vector. So this is nothing than just saying that now, if yi in the original, in this primitive representation here is equal to 0, in the one-shot representation, you represent this by a new label, which is a vector with a component 1, then 0, 0, 0, and here you have m-1 zeros. Okay. If instead in the original representation it is a 1, then in the one-shot representation this is 0, 1, 0, 0, and here you have m-2. Okay, so just in the one-shot representation, you have each label is a vector of size m. Okay. Now the labels are vectors of size m, actually binary vectors of size m, with a single non-zero component at a location which represents, okay, at the index which is non-zero encodes the class. Okay. So if you have a 1 at the first location, it means that this is the first class. If you have a 1 at the second component, it means that the label corresponds to the second class or the second category, okay, etc. Is it clear? Very simple. Okay. All right, so now that we have this one-shot representation here, in softmax regression, it's almost as before, as in logistic regression. We will again, so it's still a probabilistic model. So what we want our model to output is a probability, okay? We want to know what is the probability that some sample belongs to a class or to another class, okay? We don't want a hard decision, but we want to make to have a soft decision boundary, so to output probabilities. Okay. You remember the perceptron is a hard classifier. You output -1 or 1, so you lose completely the information of how close you are from the boundary decision. While a soft classifier, like the logistic regression, outputs a probability, which is equivalent to measure how far you are from the boundary decision. Okay, so here we again want a soft classifier, which has actually the same form as the logistic regression. So now the model is that the probability that, let's say, let me call the original labels in the original representations y tilde, and we encode them with the one-shot representation, the equivalent one without a tilde. So the probability that y tilde I, let's say, is some x, or no, not x, that's a very wrong choice. Let me call it t, where t belongs to 0 up to m-1, given our parameters and a sample xi. This is the same thing as saying that in the one-shot representation, or here I will put a little m, sorry. That yi component m is equal to 1, okay? Okay, and implicitly when I write this, the component m is equal to 1, while all the other ones are equal to 0, okay? In the one-shot representation, you have always one component which is equal to 1, okay? All the others are equal to 0. The model is that this probability is like a logistic, Okay, it's again an exponential minus xi transpose theta. Okay, but now this theta will be indexed by m as well. We'll have a different boundary decision for each class. Okay, now we are not dividing your space into just two subspaces. You have multiple boundary decisions. Okay, because you have multiple classes. Say it again. Yes, yes. So here, this is the probability that this sample belongs to the class M, okay, which is a non-zero. It's some number between 0 and 1. But maybe if you would change, okay, let's say this is a new fresh sample, okay, and you have trained your model, you are feeding it, and you want to evaluate these probabilities. For different values of M, which means for different classes, you will output non-zero numbers, okay? So maybe for the class number 25, this probability will be close to 1, while for the other classes, it should therefore be close to 0. Okay, because the sum of these probabilities should be equal to 1. Okay, so let me write the model, it will become clear. Say it again. A condition that what can be 0? No, but this is I said it orally. When I write this implicitly, this means that all the other components are equal to 0. Okay, this means component M equal to 1 and the other components are equal to 0. Okay, so if you want me to write it one time explicitly, okay. Okay. By the way, this okay, I will mention that later. Okay, let me mention, I will mention it later, right now. I think this question that you asked actually led to a confusion in the author's mind, and they did actually a typo. There is a mistake in the notes. So we will see the mistake, and I think, which is connected to your question. Okay, so you see that this probability is normalized. In which sense? It's normalized in the sense that if you are summing over all possible values of M here, these probabilities, okay, it will give 1. Okay. All right. This means that if this number if the numerator is very close to 1 for a certain class, it will be necessarily very close to 0 for the other classes. Okay? Okay, so concretely, sum over m equals 0 to m minus 1 of these probabilities is equal to 1. Okay, it's properly normalized. Okay. So here you see that these probabilities are a function of this theta, which is not just one classifier. It's not anymore a vector, this theta. It is a matrix. Okay. This theta is theta 1, theta 2, or actually, theta 0, theta 1, up to theta m minus 1. Okay, you have one classifier per class. Okay. 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 All right. So, assuming this model, again, can be interpreted in a probabilistic way. Actually, this model is a probabilistic model. So again, we can write down a likelihood associated to this model. Okay. What is the likelihood in this case? It is as before. Okay. So why am I going to write a likelihood? Because again, from the likelihood, okay, we can define a procedure for learning, which is maximum likelihood estimation. Okay, we will maximize the likelihood given our data. We'll maximize it over these parameters. Okay. So what is the likelihood? The probability of my labels. Let me write like this. Given my matrix theta and my design matrix, my matrix of inputs X. Okay. Again, as always in machine learning, it's a product over the samples, which means that we are assuming that our samples are IID. Okay. And here, now we have a product over m equal to 0 up to m minus 1 of probability of y I m equal 1 given theta and xi. Okay. To the power y I m. Okay. Which means what? Which means that in this product, only one term will be selected. Okay. Only the term where yi component, it's only the component for which this vector will be equal to 1 in the one-shot representation. The associated probability will be taken into account. All the other ones will be set to 1. So in the product, they don't matter. Is it clear? Okay. So you see here now, before, this expression in logistic regression had a simpler expression because there were just two possible classes. And therefore, the function that appeared here was simple. Okay, the only thing we could write down just as a function, just using this logistic regression. Here, the form is slightly more complex, but you see that the physical motivation, you remember for the logistic regression, we've seen that this form was very natural if we think in terms of system with two possible states, the statistical mechanics with two possible states with two different energies, a two-level systems. And the function that appeared here in the case of logistic was just the Gibbs measure, you remember? And here it's the same. We have again a Gibbs measure, but now it's not anymore a two-level system. It's a M-level system. And the normalization here is the partition function of these M-level systems. And the energy of each state is of this form. It's again a linear combination of the features. It's just that the linear combination here is different for each of these states. And it's defined by this classifier. Okay? So it's a very natural generalization. It's exactly like logistic. Now we have M states. Okay? But we have again this exponential form, so it's really like before. Okay? All right, so if you look at the notes, this is not what they wrote. They wrote something wrong, and I triple and quadruply checked. They are really wrong. They wrote something like this. Okay. You can very simply convince yourself that it is wrong, and I will not spend time on why it is wrong, because with high probability I will confuse you more than make things clear. The very simple way to see that they're wrong is that if you include this thing here, you don't recover logistic regression. Okay. You see, if you have a product over M here, if you have just two states, like in logistic regression, you will have the probability that the first one equal to, that the label here is equal to 1, times the probability that it's equal to 0 with 1 minus y, which is indeed what you recover here in the case of M equal 2. So I don't know what they did here, but they got confused, and this term here should not be there. Okay. The only possible explanation I see why they could have added this term, it's because maybe in their mind, in their representation, it's not because you have a component in the one-shot representation that is equal to 1 that necessarily the others are equal to 0. Okay. In this case here, if you want, this means the probability that a component is equal to 1 and that the others are equal to 0. And if you make this product, this probability indeed construct. But this is not correct. This is okay. This is not. So really, when one component is equal to 1, all the others have to be equal to 0, and this term is not here. All right. Okay. So this is our likelihood. Great. And now, as before, okay, how to define the cost, which is now depending on this matrix theta, okay, where each of this one depends. Theta 0 belongs to RP, theta 1 as well, etc. Okay. So this matrix, if you want, belongs to RP times M. So the cost now is the log likelihood is minus the log likelihood associated to that. Okay. Therefore, is equal to minus sum over I, sum over M okay. Okay. And here again, in the notes, they have this term, okay? And they write, as expected for m equal 1, we recover the cross entropy for logistic regression. Unfortunately, no. You indeed recover the cross entropy of logistic regression when you don't have that term, okay? Okay, so always be critical with everything you read. If it looks weird, it's because maybe sometimes it is weird. Okay. All right. Is there any question on that? So it's a very simple generalization, right? From logistic to softmax. So the motivation from a statistical mechanics point of view is exactly the same. We have the Gibbs measure where energies, the energy of a state is of the form of a linear combination of the features. But now for each state is defined by a different linear combinations. And you are trying to learn what are the proper coefficients in this linear decompositions, okay? And the way to obtain the cost, as always, here is to define the log likelihood associated to this model, okay? And we are trying to maximize the log likelihood, or equivalently to minimize minus the log likelihood, which means to maximize the probability of having obtained the labels that are in our training data according to our model, okay? And to maximize that with respect to the 3 parameters of our model, which are the theta's here, okay? Okay, so if there is no question, essentially this is everything I wanted to say. So now, now I would like to, so is there a question from internet? Okay, seems not. So what I would like to do now is to discuss a bit what I expect for the numerical project. Okay, so I detailed everything on the mail, but let me detail a bit more so that it's very clear what you have to do. Okay. Do you want to take a 5-minute pause or as you want? It's okay. We continue. Okay. You want? Okay. I also want to be in weekend faster. Okay, we're on the same page. Okay. So now you have actually all the tools to solve real problems in machine learning. Okay, so this is not yet neural networks, but let me emphasize that in maybe 90, probably 95% of applications in the world with real data, okay, what people are actually using is what we discussed in this course. There are linear regression, logistic regression, softmax regression, simple things. Okay, to exploit the power of more, fancy techniques and neural networks and things like this, these techniques make only sense in specific applications where you have really huge amount of data and for very complex data. Okay, but also, like we discussed, sometimes complicated or complex methods suffer from overfitting. Okay, you have many parameters, so if your data is not big enough, you don't have enough data, or it's not of good quality, it can be a mistake to use complicated models. Okay, because complicated models may be less robust to noise. Okay, to sampling noise, to the fact that you have a small amount of data. Okay, so in most of the case, simple algorithms are good enough, and actually they can beat more complex methods. Okay, of course, what we did is a very small sample of the techniques that actually exist, but in many cases it's sufficient. You don't have to always go for the most fancy technique. Okay, and also from the conceptual point of view, once you understand what is doing logistic regression, you're not so far from understanding what are doing neural networks, at least at high level, because neural networks are sequences of logistic regressions. Okay, put one after the other. You are just defining many more different hyperplanes. Okay, so you are cutting your space in more and more complex shapes. Okay, because you see logistic regression is just dividing your space in two parts, right? It's a hyperplane. So you see that if you have enough hyperplane, you can cut your space in whatever shape you want, right? So a neural network is learning many hyperplane in order to divide your high dimensional space into subparts in a complicated manner. Okay, but the basic unit of a neural network is a neuron. What is known is what we studied here. Okay. Okay. All right. So for the project, what I would like you to do is to code from A to Z. Okay, from first line to last line, a logistic regression and a softmax regression. Okay. In different settings. So the first setting I would like you to explore is the realizable setting, realizable rule. Okay. So what is the realizable rule setting? You remember we said it's when your hypothesis class includes the actual model that generated the data. Okay. So logistic regression is a linear model. Okay. So the output in this case, which is a probability, this logistic function applied to a linear combination of features. Okay. So if we want to be in the realizable setting, what does it mean concretely? We need to have data which is linearly separable. Okay. So logistic regression is a linear model. Okay. Which means that we need linearly separable data to be in the realizable root setting. Softmax regression is more advanced. You don't need necessarily linearly separable data because you have multiple hyperplanes. Okay, so you can cut your space in more complicated ways. Okay, but if you use logistic regression, we're talking about just two possible classes, and if we want to be able to perfectly predict, so to perfectly fit data with binary labels, okay, this data has to be linearly separable, which means that there must exist a hyperplane which divides perfectly this data set, okay? So how can we generate some data and make sure that this data is linearly separable? So we want to create an artificial data set. Because in general, of course, data is not linearly separable, maybe approximately, maybe almost perfectly, but realistic data is generally not linearly separable, okay? So I want you first to code logistic regression on an artificial data set that you will generate. So how can you make sure that your data is linearly separable? So you should know because I explained exactly how to do in the mail. Sorry? Yeah, so what you can do is it's very simple. You will generate samples, okay? So let's say you generate IID samples xi, okay? For example, this could be Gaussian vectors, okay? Or with binary components or whatever you want, okay? Each sample is a p-dimensional, okay? Each component is interpreted as a feature, okay? So you can generate totally random vectors. And how to make sure that these vectors will be linearly separable? You can create the associated labels, okay, according to a linear rule, and that's it. Okay, so then generate, I will call that a ground truth theta, maybe theta star, okay. Using what? Building function. I don't know what is a build. The what, sir? A built-in function. Yeah, but I don't know what you call built-in function. But I mean, if you need to generate random Gaussian numbers, for example, you can use a. I'm not asking you to code a generator of Gaussian random numbers. No, yeah, if this is the question. No. Okay, no, of course. No, I mean, this is, use your common sense, okay? I mean, okay, basic functions like random numbers generators are things that you can and you should use, okay? Of course. I mean, people are doing entire PhDs on how to obtain good random numbers generators. It's a very complicated task, huh? Okay. All right, so generate a ground truth theta star. So this theta star can be also random according to the distribution you want. And then generate the labels. According to this rule, okay? Or if you want to make them 0, 1, for example, you can do +1/2, okay? So in this case, you are sure that there exists a hyperplane that divides your data perfectly. And this hyperplane is this theta star, okay? It's clear? So now you just obtain your data. Okay. Oops. And this data by construction is linearly separable. Okay. Because there exists theta star, there exists a hyperplane parameterized by theta star that perfectly separate, okay, this data in two classes. Okay. Sorry. You choose what? The number of features? Yeah, yeah, of course. Of course, you should mimic, high dimensional settings. P should not be 5, it should be maybe 1000 something. Okay, and now from this data set, okay, you forget theta star. Theta star is not given to you anymore, okay? And you need to train a logistic regression in order to classify this data, okay? Now, train a logistic regression by SGD, and you can compare with NAG, okay? The two type of stochastic gradient descents that we talked about. Okay, and what does it mean training the logistic regression? It means defining the cross entropy, okay? So you have to write down the cross entropy. And actually what you really need to write down is the gradient of the cross entropy, because what enters the algorithm in SGD is really the gradient of the cross entropy, okay? And this we computed, okay? But actually, now I want you to do something slightly different. Train a logistic, and I will here put a penalized, L2 penalized logistic regression. What does it mean is that the cost will be the cross entropy plus L2 penalization. Concretely, it means what this? Okay. So what does it mean probabilistically speaking here? If you always should try to think when you define a cost function, what does it mean in Bayesian terms? Okay. If your cost is a cross entropy plus a L2 penalization, what does it mean? What are you assuming from a probabilistic point of view? No, go for it. You don't know? You should know, huh? Say it again. Yeah, it's correct. What you are assuming is that the likelihood is given by the likelihood associated to logistic regression, okay? And that additionally, you have a prior. And the prior is that the theta were drawn from a Gaussian measure, okay? I think it's the... Okay. And you are not anymore doing maximum likelihood estimation. You are doing maximum a posteriori estimation, okay? This comes from the prior, and this is the likelihood. Okay. So this is a generic advice, but so, you know, Bayesian statistics, which we discussed a bit, okay? Whatever you will do as a PhD, okay, from now on, maybe you don't do a PhD, but like this is absolutely crucial, okay, to any science, to anything you will do, okay? You should make the effort now to be clear with some Bayesian statistics, okay? The things we discussed in this course, likelihood, prior, base formula, okay? All that should be, now it should be easy for you. Huh? This is very important, very, very, very important, okay? Okay. So you see that you have to do the exercise again to write down the gradient of the cost, because this will be part of your code in SGD, okay? But actually, you could guess what's the gradient here almost, because this is the gradient of the cross entropy that we already derived, plus the gradient of this term, which just gives a linear contribution in theta. It's very simple, okay? It's the cross, it's the old gradient plus a theta, okay? Okay, so exercise, which is not very exercise, it's very simple. Compute the new gradient here, okay? But this is almost the same as before, because you have almost the same cost up to this new additional term, okay? So I think it should give something like plus theta plus lambda theta, something like this, okay? Okay. So in this realizable setting case, if you have enough data, if you have a lot of data, you should be able to perfectly reconstruct at some point the theta star, right? The ground truth theta star. So you should see this effect. And if that's not the case, it means you have a problem. Okay? Because your data is noiseless in this case, it's clean data, and it is linearly separable. So if you have enough data, at some point you have enough constraints to perfectly find the hyperplane. Okay? Actually, perfectly, let me correct what I said. If the theta star is discrete, belongs to a discrete set, let's say it is binary, for example, it has binary entries, at some point you will perfectly reconstruct it. If it is real, of course, it's only in the limit of infinitely many data that you would reconstruct it perfectly. Okay. Okay. Now, once you have done that and you have tested your algorithm on this very simple data set on which you should be able to perfectly predict, okay? So of course, on all that, you have to follow the machine learning workflow, which means that you generated this whole data. You have to divide this whole data set into training data, test data. You train on the training data, and then you test on the test data, okay? And also I ask you to do cross-validation. You have to select in some way the value of this regularization strength. So you have to do all this process for different values of lambda until you find, and for each values of lambda, you plot the training error that you got, the test error that you got, and you should find the optimal value of lambda where the overfitting is the lowest and the test error is the lowest, okay? So in this case, the good error metric is the accuracy, is the fraction of samples that you correctly classify, okay? Rather than a mean square error, here we are just checking if we are correctly classifying. So don't use as an error the mean square error. Okay, the way to judge is by counting the number of examples that you correctly classified divided by the total number of examples on which you tested. Okay. It's okay. You understand? Okay. If at some point there is something you didn't understand, or you send me a mail, okay? I will not send you the code, but okay. Okay, and then once you did that on this simple data set, after cross-validation and all that, like the full clean experiment, try on that on realistic data, on real data. Okay, so download the data set, whatever data set you want, and implement your algorithm on this data set. Okay, again, you follow the usual workflow: division in training and test data, learning, cross-validation to find the proper regularization strength. And once you find the perfect regularization strength, you obtain some results and you're happy. Okay, and maybe you see that the data you downloaded is almost linearly separable, in the sense that you will have a very high prediction accuracy. Maybe not. Okay. What does it mean? I mean, geometrically, the picture you should have in mind, data that is linearly separable, for example, in 2 dimensions. What does it mean? It means that you really have 2 classes. Okay. And there exists a plane here, a hyperplane that perfectly separates these 2 classes. Okay. Now, if I draw data in 2 dimensions, which is not linearly separable, could be, for example, okay, this is clearly not linearly separable. Here, the boundary decision is an ellipsoid. So you will never find a hyperplane that correctly classify that. Okay. But something a bit magical is that in high dimension, things usually are not too far from being linearly separable, because you have so many directions and degrees of freedom, so many directions in which you can move around your hyperplane, that you can often find a good enough hyperplane. Okay. So data in high dimension tend to be more linearly separable than in lower dimension. Okay. And yes. So often what people do, okay, it's the idea behind kernels and all that, but even without kernels, people are often doing some point I mentioned. So random projections. So for example, you take your data and you project it in a much higher dimensional space, which are random features. So you, for example, you apply a random matrix to your data. Okay, a very tall random matrix, which means that you are projecting something which is maybe high dimensional into an even higher dimensional space, which is a random. The space is random in the sense that you project your data in random features. Okay. And by projecting this data in random directions like this, you are spreading around the data in a very high dimensional space, much higher dimensional than its original dimension. And the hope is that by doing so, you will be able then to find a linear classifier in this new very high dimensional space. Okay. And it works very well. Okay. Okay, so for example, the data sets you can consider could be MNIST. You know MNIST? Okay, you know MNIST. Actually, I see that in notebook 7, this is exactly what they do. I forgot that actually it's done there. So please don't, I mean, you can look at the notebook, but this, I mean, it won't help you much because in the notebook, they use the packages of scikit-learn and all that. So they use black boxes, so it won't help you. What I'm asking to you is to code all the pieces. Okay, so you can have a look. It will not help you in any ways. Okay, maybe it helps you to know how to download MNIST, but that's it. Okay, so what I ask you is to code. Yeah, I already sent you how to do, and actually I copy pasted from this notebook. So what you have to do is to code everything. What does it mean? Everything, the SGD, the part in SGD that create the mini batches randomly, to do the splitting of the data, to, you know, everything. Okay, and honestly, it's not so long. It's it's a code like this. It's maybe I don't know. It's 200 lines. Okay, it's nothing. Okay. So then test your codes on MNIST. But MNIST, for example, the MNIST data that you download, there are 10 classes. There are 10 different numbers. Okay. So if you want to test logistic regression on MNIST, what you can do is to select in these 10 classes only, for example, the numbers corresponding to 4 and to 6. Okay. And to train on this data and to try to classify the 4 and 6s. Okay. Okay. So you will see, just Google a bit, the MNIST data set is you can easily try to extract what are like 2 numbers. You have to extract 2 possible numbers. Okay. It took me an hour to understand how to do, but I did it. So you should be able to do it. Okay. But you can consider other data sets if you want to try on images. Okay. MNIST are images actually, but you can take other images. Okay, if you want to test on pictures of you, why not? You take. I mean, you can take plenty of pictures of you. I don't know. For example, if you had a lot of time to spend, you take tons of pictures of each of you, and then you try to classify who are girls, who are men, for example. Or no, yeah, you can do soft math. Yeah, but it's difficult because maybe there is one of you each. There is one person per country, so you don't have enough examples. So while you are approximately half and half men and women, so you can do a classification there. But okay, I mean, take data on internet, okay, whatever you want, and do a binary classification, okay? So, for example, when I did this exercise, I noticed, and you should notice the same, I think, is that, for example, MNIST, and I was very surprised, you take any 2 numbers in MNIST, it is almost perfectly linearly separable, in the sense that if you train your logistic regression on MNIST, you obtain amazing results. And I thought I had a problem, like a bug, but no, that's really the case. I mean, you obtain super good prediction performance with the logistic. Okay. And then repeat all that and do a soft max regression. So try data with more than 2 classes. Okay. And basically that's it. But what you have to make the effort of is to have a clean code. Okay, because I will. No, but because this is not just because I will have a look, and it's because later when you code and you interact with people will never do the effort of understanding what you wrote if you don't write it cleanly. Okay. And let me be even more extreme on that. If you will very quickly not understand your code anymore if you don't look at it for a year. But that's really true. Even simple codes. Huh? No, but no, that's true. I mean, No. It's impossible. You have really to make the effort to make it clean in order to reuse it later, okay? Even not without talking about other people, even for you, okay? So essentially, I want to see something that I don't need to mail you, what are you doing there, okay? You have to comment what you are doing and to make the code compact and clean. And okay, I just have to run and to see the results that are plotted and okay? Like the notebooks that we, okay? And if you want to add text, you add text there in the cells and okay? It must be in the form, take examples in the notebooks I sent you, okay? Must be that clean, okay? And that's it, okay? Let's say in 2 weeks, okay? Honestly, it's really okay. Don't worry, it's not too much. Okay, basically that's and if for some of you it's too simple and I hope it will be no, but honestly it's not complicated. And what is nice is that it will be the only time in your life where you will code these things, okay? Because then you will never anymore code an SGD or a logistic. Everything are packages. So do the effort and take it as an opportunity for you to understand what is going on. But if you want to be original, you know, and to code something else and use exotic data, whatever, I'm very happy to be surprised, okay, by your the application that you consider, okay. Okay, so that's it. So no question on internet, like, okay. So for those who are here on internet and are interested in following these discussions on neural networks, so we will start that maybe, let's say, after the project or or now? Okay, so after the project in 2 weeks, we start meeting for discussing this book, okay? About? How do we reach out? What do you mean? No. Everyone, it's automatic. I will send you. So I will send you the link for the book again, and you can start reading. Okay, and so after the exam, we start meeting, and maybe every 2 weeks, every week we do 2 chapters, and that's it. In 3 weeks, it's done. Okay. Yes. And so I will stop the camera.